I'll start off by summarizing little bit on what I spoke about in the last 2 lectures. So, it was on pulsed lasers. So, I spoke about the single pulse laser. Okay, this single pulse laser here, this diagram you have seen even before. So, you have one pulse which is coming out, and a single pulsed oscillator is a relatively long pulse. It is called a pulsed laser, just a pulse laser. And what happens is you are pulsing the pumping medium. Okay, the pump medium you pulse it. Okay. So, obviously your output will also be a pulse. Okay, that is all you have got to do. In a resonator you are pumping the active medium in a pulsed mode. Say in case of a carbon dioxide laser, which is a gas laser and a discharge is passed through it. So, you pulse the discharge, you give one pulse and the discharge glows and you have an output pulse. So, these are called single pulsed lasers, but they are not always very clean pulses. What do I mean by clean pulses? You just might have say not just one pulse, there may be some small pulses and then another one will come. So, it depends on how clean or how accurate is your pump pulse. Okay, how accurately you are pulsing your pumping system. Okay, so, it depends on that. So, you will get this sort of a unclean kind of a thing. So, the next thing I spoke about is the single pulsed Q switched. So, Q switch is the method where you get a giant pulse at the output. Okay. This pulse is slightly shorter than say the pulse here from a single pulse. This system is called a free running system. Quite often it is mentioned that way. And so, a Q switched oscillator pulse, okay, here Q switched, will be a slightly shorter pulse than the one that you get here. Okay. And it can be categorized as a short pulse. And more or less it is a cleaner pulse than the previous one. So, you will get just one giant pulse. Okay. And this pulse width is shorter than this pulse width. Okay. So, that is what I mean, and that is why you call it a short pulse. Next, if you want to go to an even shorter pulse, the method, as I have said, is mode locked pulse. I will be speaking in details about this mode locked system and even the Q switched system, but here it is just to say that a mode locked oscillator pulse is even shorter than a Q switch pulse, and it falls under the category of ultra short pulses. Okay. So, you will soon come to know what I mean by short pulse and ultra short pulse. Basically, I will give you some exact figures which tell you whether to call it a short pulse or to call it a long pulse or whatever you like. So, this was the summary of my previous lecture, and now we go into a little bit more detail of what is a Q switched pulse. Okay. So, it is a very important method of getting pulsed lasers. Okay. So, before I get into Q switching, I have to define the property that is a quality factor. The Q factor of a cavity, it is a dimensionless quality, dimensionless property, but the thing is it describes to you how the cavity, your resonator cavity, how good is it or how bad is it, okay, within the duration of one cycle of the pulse. So, what do I mean by good or bad? I have pumped in some amount of energy into that resonator cavity, And is that resonator cavity able to store all that energy that I have pumped into it, or it's not a very good cavity and it's unable to hold on to the energy that has been pumped into it. Okay. The Q factor is defined as omega 0 here, that is the frequency, that is the oscillating frequency of the mode. Okay. So, omega 0, and it is the energy stored in the mode, in this mode, because that is the one which is oscillating or lasing, and the energy lost per unit time. Okay. So, this is what quality factor is defined as. Suppose I have a cavity with two mirrors on either side and they are 100%. There is no chance of any leakage from the mirror. Whatever be the emission or the slight light that comes out due to spontaneous emission is all trapped within these two mirrors. So, it is 100%. And even the walls of your active medium does not allow any losses. Just assume hypothetically that it's absolutely, it is mirror polished, nothing comes out of that. So, you do not have any losses from the output mirrors and you do not have any losses from the walls of your active cavity. Okay. So, that, and suppose that cavity is just a free space, okay, and you have been able to pump in this energy, no energy is lost. Okay. So, this is a very ideal condition, but it never ever happens in real life. You can't make mirrors which are 100%, they are always 98%, 99.9% or 98.9%, whatever. So, there are certain losses, and then as I have even spoken about it before, there are losses in your active medium also. Your spontaneous emission may just move towards the walls of the active medium and get lost. Okay. So, then we have to describe, we had described earlier a quantity which will talk in terms of these losses. So, putting it in mathematical terms, this formula, I can say Q is equal to omega 0 and Wt is the energy in the mode at the time t, Wt, that is the energy stored in the mode, and it is energy lost per unit time, dW by dt. Okay. So, energy watts lost per time. Okay. This, as you can see, is a differential equation, and it is quite a standard one, and its solution is given by this. You have come across these solutions many times before, and I myself have given it in quite a few of the previous slides. So, the energy at any time t in that particular mode is equal to W0, which is your initial energy that you have pumped in at time t, e to the power minus W0 by Q by t. So, now I want to define one parameter called Tc, which is the cavity lifetime. That is the time in which the energy in the mode decreases by a factor of 1 by E. Now, why do I describe such a quantity? I want to describe this quantity because when I am storing all this energy into my resonator cavity, all I have to ensure that most of this energy remains in the cavity till a round trip time, or if not a round trip time, till the time the total energy is extracted out in the laser pulse. After that time, I have there is no need to define a quality factor. Okay. So, you have increased, that is why you need this parameter of Tc, that is the cavity lifetime. So, the cavity lifetime in which the energy of the Q, the energy within the cavity reduces by this factor. Ideally, we would not want it to reduce at all, but because it is a real system, it does reduce. So, we have to quantify this reduction. So, Tc is defined as q by omega 0. Okay. Maybe when you substitute this Tc in this equation, so it just becomes e to the power minus T by tau c. Okay. So, that is just another way of writing it. Now, I want to derive a formula for q. I want to know exactly what q is, because I want to design a laser oscillator, and in order to design that I must know the q. So, what is the formula for q? The quality factor. So, to do that, to calculate the quality q of a resonator, let W0 is the energy within the cavity at time t equal to 0, something like this, something in W0. R1 and R2 are the reflectivities of the mirrors, okay, as I have said, and gamma is the power attenuation coefficient per unit length. Okay. So, this is the attenuation which is getting lost at the walls of the active medium or wherever, and the length of the cavity is d, we define it as d. I have defined these even before when I was speaking about resonator, it is more or less the same thing. After one round trip, the energy in the cavity will be W0, which was the initial energy. It will get lost at R1, the mirror 1, as at a rate of R1. It will R2 also will be lost at mirror 2, some losses in mirror 1, some losses in mirror 2, and in general loss because of the gamma factor, okay, the power attenuation e to the power minus 2 gamma d. This expression will look very, very familiar to you because it has been derived previously. Okay. So, this gives you the loss in energy. Okay. And then if you do a little bit of jugglery, you can write this as this. I write it at this because you put the term e to the power ln R1 R2. Basically R1 R2 I have put it as e to the power ln R1 R2 minus 2 gamma d. So, all in this exponential part, because it is a loss term. So, you know how much of this initial energy W is lost. This is again a familiar formula to you, which was derived earlier, a few slides earlier. You can go back to it and just confirm that. One complete cycle corresponds to the time interval TR. Let us call it just TR. TR is one complete cycle. From one, it starts off from one end of the mirror, goes through the other mirror, gets reflected into the next mirror and back. So, that means it has traversed the active medium twice. Okay. So, TR is 2 N0, N0 is a refractive index, you can make it 1, 2 N0 d by C. Okay. Now, the energy at the end of this one round trip, omega t, TR is equal to W0 exponential minus omega 0 by Q 2d N0 by T, N0 by C. Okay. Basically, this expression is, I have just taken this expression itself and substituted in place of T, I have substituted TR. So, substituting TR in this red equation, you get this sort of a thing. Okay. Now, compare this red equation with this blue formula. Just compare it, they both look about the same thing. Within the, so W and W0 is here. Now, suppose you can equate this part of the formula with this part of the formula. Okay. So, you have ln of R1 R2 minus 2 gamma d is equal to 2d omega 0 N0 by CQ. So, the final, and from here this is the final formula for Q. Just look a bit closely at it, you will find all the losses are here, these are all the loss terms. So, if the losses are very high in the cavity, then your Q becomes very low. if the losses are low, then the Q becomes very high. Okay. So, you would like to keep the losses to be low, so that your Q is high. Okay. But at some time or the other, maybe the Q also becomes low. That is what we will see in our next slide. Okay. I have just put this down here. The technique of Q switching just depends on this. When loss is low, Q is high. When loss is high, Q is low. In Q switching, you are just switching from this mode to this mode, this mode to this mode. It is just a switch between this to this. So, the term Q switching was termed. From high Q to low Q, high Q to low Q, you are switching in order to get a Q switched pulse. So, this is called the Q switching method. So, let me go back to the resonator again. So, here this is the resonator with mirror M1 and M2, and this is the active medium, AM is the active medium, and S is a kind of shutter. Okay, for the moment you assume S is a shutter. It is a shutter, some specific type, not any mechanical type as I have described before. So, resonator with a shutter and these two mirrors. Now, how do I switch Q? Okay. I am pumping in all the energy here. The Q has become high, then I open the shutter. I just open the shutter and the whole population inversion that has been created in this active medium just falls down to the lowest level, and all that energy is transferred into my pulse, and the pulse comes out. At that time, within this cavity, the Q becomes very low. So, the moment you get a laser pulse out, your Q of the cavity becomes low. It has switched from high Q to low Q. So, what I get out is a Q switched pulse. Now, how does this shutter work? That is the question. Okay. Quite often it is a shutter like this, which this picture I have shown before. There is a Optical cell in between, and there are two polarizers. Just in brief, let me explain what is a polarizer. Okay. So, a polarizer means unpolarized light, which I have depicted this way. That means it has it is oscillating in all directions. The field of the light is oscillating in all directions. It is not in just one plane. It's all in the three planes it is oscillating, okay, that light. Then it passes through this light, it passes through a polarizer. P is the polarizer. I have depicted it as a sieve, a kind of a sieve. So, the light that can pass through this is the one that is vibrating in one plane. It has oscillations in one plane. Okay. The other one, the one which is a perpendicular plane, this does not allow it to pass through. So, it is a very crude way of putting what a polarizer is. A polarizer, the actual optical polarizers are quite complicated, but very clever method of making a polarizer. So, one direction of polarizer is direction of vibration of the light is allowed to pass through this polarizer. So, I have started off with an unpolarized light, but at the end of the polarizer I have a plane polarized light. Okay, this is shown as a plane polarized light. I can have another polarizer which may be perpendicular to this. So, the perpendicular direction of vibration of that wave of light, that means this is allowed to pass through, while the horizontal polarization of that light is not allowed to pass through. Okay. So, here I have a horizontal polarization, here I have perpendicular polarization. Okay. Sometimes it is called P and S polarization. So, if I call this S, this will be P. They are perpendicular to each other. So, I start off with an unpolarized light, any light, unpolarized light. I pass it to polarizer, and depending on the orientation of the polarizer, I will get a polarized light in whichever direction I require. Okay. So, all you have to do is to orient this polarizer in a way that is suitable to you, what you are looking for. So, this one is the polarizer, this is also a polarizer. Okay. So, generally they are crystals, something like quartz, okay, which can separate out these polarizations. Okay. So, this and this, say quartz crystals, they are able to polarize this light. Okay. So, what is done, how will this shutter work? The shutter consists of, suppose I have unpolarized light from this side, this shutter will polarize it, it will go through the Pockels cell. Now, the duty of the Pockels cell is to rotate the polarizer, rotate the polarization. It rotates the polarization, and then this shutter just does not allow that polarization to go through. Okay, because see, this is oriented in a different way than this. If this is allowing through and this is not allowing through, okay, that is the thing. So, what you have to do is the two polarizers you place in place of that shutter. So, the lasing light that is coming through, or the spontaneous emission, or whichever is the spontaneous light that is coming through, you know, it does not pass through the shutter, because these polarizers are crossed with each other. Okay. This is called crossed with each other. That means, if one polarizer passes, the other one will not let it pass. Quite often it is called polarization and polarizer and analyzer. Okay. So, they are made perpendicular to each other. Okay. So, that light, this polarizes it, and this does not allow that polarized light to pass through. So, initially your Pockels cell is allowing that light to pass through. Now, this Pockels cell is an electro-optic switch, EOS in short, electro-optic switch, which works something this way. You have a crystal, you apply a voltage, and you create an electric field here, and once you create that electric field, one polarization is rotated from, say, perpendicular to horizontal, it will become. If it is horizontal, it will become perpendicular. So, it rotates the polarization by 90 degrees. Okay, that is the job of the electro-optic switch. So, now you have to apply a voltage between these two, this electro-optic switch, such that it rotates the polarization. So, when I begin with, I have one light which is coming in this medium, it comes to the shutter, that means it comes to this polarizer, it gets polarized, the Pockels cell is not on, no voltage is applied. So, and this polarizer is crossed with this, so it does not allow the light to pass through. So, it does not reach mirror to at all. But the moment I apply a voltage to this Pockels cell, it rotates this polarization, and this polarizer allows it to pass through. Initially it did not allow because it was in cross. Now the Pockels cell just allows it to pass through. So, this is it acts like a shutter. So, you apply a voltage for a short time, whatever time you want, you apply it for a short time, and say the shutter is open then you close it, you do not apply the voltage, and the shutter is closed. So, that is how the electro-optic switch works. So, you have the shutter opening and closing at your will. So, when the Q is very high, the shutter is closed. Then you apply a voltage to this electro-optic switch and the shutter opens. And the Q comes down and you have a large pulse. Okay. And then immediately after that you can shut it off again if you want the next pulse to come in. So, now these shutters can be either an electro-optic switch, or it can be an acousto-optic switch, or it could be a saturable absorber. There are these three types of switches, they are all switches. During the course of the next few lectures, I will describe what is an acousto-optic switch and what is a saturable absorber. Some of the crystals that are required for this electro-optic switch is cadmium telluride. Generally it is used for carbon dioxide laser, which is in the 10.6 micrometer range wavelength. You know, these crystals you have got to choose depending on the wavelength that you want to use it for. KTP or potassium titanyl phosphate. This is used generally with the ND glass or ND YAG laser. Okay. Then you have beta barium borate, BBO crystals, which are also used as electro-optic switches. Then you have lithium niobate, which are also used as electro-optic switches. In case of the acousto-optic switch, the principle used is as follows. There is a medium in which you create with sound waves, you create a sort of a grating in that. You form a sort of a grating. The moment that grating happens, the light that is coming to the grating, obviously it will get deflected off. And quite often, suppose you've placed this acousto-optic switch here, the light comes in from here, and because of that grating that is formed, you know, the light is just deflected back, deflected off, and it does not reach this mirror at all. The moment you put off that acousto-optic signal, the grating also disappears in that medium. The moment the grating disappears, the light goes through and comes to this mirror M2. Okay, and then you have the lasing action. So, basically that is another method of switching on and switching off, another method of saturation, another method of a shutter. Saturable absorber is also a kind of shutter. Saturable absorbers are called passive shutters because there is no electrical signal or anything required for that, while EOS and AOS are active shutters. Okay. So, I end here, but in my next lecture I will give you a little bit details about saturable absorber and acousto-optic switches, and we will go through some of the pulses and the durations that we are looking for. We are looking for shorter and shorter pulses. So, I will describe, I mean, in which medium you get a short pulse, which medium you do not get a short pulse, and how Q switch helps in obtaining these short pulses.